Okay, in this video here we're going to look at doing kind of a transient and steady state response of a circuit here. So we're going to look at a very basic circuit. We're just going to look at a series circuit with a resistor, inductor, and capacitor here. So let's go ahead and build the circuit here. So we really just need some of my analog components. I need a resistor. And there we go. And then I set an inductor. And then we also need a capacitor. And then I'll rotate this. And so I'm going to kind of move these things a little closer. I'll even zoom in here. I don't need to be this far out. And so we're going to go ahead and set these values here. This is going to be a 90 ohm resistor. And then this is going to be a 32 millihenry inductor. And then this is going to be a 5 microfarad capacitor. Now we are also going to put in, well, we're going to put in a sinusoid. So we're going to do a source here, V sine, and go ahead and put that in there. Of course we need a ground. And then we'll connect everything up here. And then we need to fill in these V offset as if we had an offset for the voltage. Amplitude, obviously that's the amplitude of the sinusoidal, and in this case it's going to be 750. And the frequency here is going to be, well, I'm just going to go ahead and let it be 1000. And it's important to know that when you put a frequency in here, it's in kilohertz. So that's 1000 hertz, or I'm sorry, not in kilohertz, and it's in hertz. So and then I don't know why, but I can't remember why, but I set the AC to 1 here. Now we can go ahead and simulate this right now, and that's what I'm going to go ahead and do. So we're just going to create a new simulation profile, and we'll call this transient because that's what we're doing. And wait patiently. There we go. Wait patiently again. Okay. So I'm not going to change anything here at this point here. Yeah, so I'm just going to leave it as is. Just leave it, not do anything. Then I'm going to go ahead here, and actually I don't want to do a voltage. I'm going to do the current. I think it might give me an error because it wants currents actually, yeah, connected to an actual pin here. So current through the inductor. It doesn't matter what pin I put it through. Obviously this is series. Okay, so let's go ahead and run this and see what happens. Okay, so we get this as the output here. Now this is supposed to be, in steady state, we know that this is still supposed to be like sinusoid, but doesn't look like a sine wave or a cosine wave here. So what's going on? Well, what's going on is we didn't pay attention to how long we were simulating this. And what do I mean by that? Well, let's go back and let's edit the simulation profile. We simulated this for 1000 nanoseconds. So let's pull up a calculator here, and let's just think about some things here. Okay, so we have a frequency of 1000. So if we're saying 1 period here, 1 divided by 1000, of course, is 1 millisecond. So 1 period of this source here is 1 millisecond. And I'm simulating for 1000 nanoseconds, which would be the equivalent of 1 microsecond. So I've not even simulated for a full period. So there really shouldn't be any, I shouldn't be surprised that there's nothing really coming out of this at all, or that the output doesn't look correct. So I need to change this value here. And so I'm going to do, well, let's just go ahead and do 1 period to start with and see what happens. Okay, so I changed that to 1 millisecond. And now we can see, oh look, I've got some stuff going on here. It looks kind of like a sine wave or a cosine wave, but again, it's still, you know, only 1 period. Let's go ahead and simulate more than 1 period. And so let's go ahead and maybe simulate 5 periods. So I'm going to do 5 milliseconds. Okay, well now it simulated it, but now it looks like it's all choppy here. And that's because it's doing automatic data point here. So let's go back here and edit again, because it's picking its own step size here. So let's put a maximum step size of, I don't know, let's do maybe 0.01. You have to be careful. You don't want to put too many data points in here because it makes the simulation take longer to do. And also, sometimes if you put too many points in there, it can't plot them all. But I'm going to do 0.01 milliseconds. So let's simulate it again. Okay, well now we get this nice sine-looking wave. But now let's look at here. We should be able to identify, just kind of at least looking in this graph, notice that it goes up here, but then it jots down really low, then comes back up, and jots down, and then comes back up higher than it was here, and then jots down, up, down, up, down. Now, we should look at here, like it goes down almost -5 at one point, goes up to almost 4 here. Now it looks like it's at 4, and then, well, this isn't quite at -4, but here it looks like I'm going between 4 and -4. And that's because I'm using the mouse here. This area right here is that transient response. You know, this is the circuit basically having no initial conditions on it. It's basically everything's already been discharged, and we turn the voltage source on at time equals 0. So it takes time for those components to reach a steady state value for us. And so I'm going to go back and simulate, and I'm going to go back here and do a little bit, whoops, that's view simulation, and do a little bit more here. Let's go out a few more periods and do 8 milliseconds. You gotta be careful how many periods you go out. But if we go out here, we can see, okay, yes, so we have got this weird business going on the front end right in here. But then over here, it's all the same. It just is a sinusoid that keeps going up and down, up and down, and up and down. Now, there are things we can measure here. There are tools here. So, what tools do I want here? Measurements. So we can evaluate a measurement here, and the current, I mean, you know, you could look at any of the currents here. We'll just say the current through it going through one here. Whoops. I want to look at, well, they have, where is it here? Period, for instance, of the current. And then we'll display down here, and it's 959.3870 microseconds. Now, of course, one thing you could do is you're saying, well, I want to know what the frequency of that is. So you could go again here to evaluate measurement, and I can do 1 divided by, and I'm going to type it in now, period, current through the inductor. And so we do that, and we get 1.04233K. So the frequency here, now you might say, well, what's the frequency? Is it measuring this frequency over here, or is it measuring the frequency up in here? I don't exactly know which one it's doing, but we can, you know, re-simulate this, and I'll show you in a second how you can re-simulate it to see if you can get a better accuracy of the period. Because we can see here, well, wait, we've got, like, let's say, all the way up to maybe 4 milliseconds, we could kind of ignore that stuff here because we could say, oh, well, wait, you know, it's in its transient spot. So what you can do is you can go back to your simulation profile and say, start saving data after 4 milliseconds. Because basically what that's saying is, okay, I'm going to wait for it to get into the steady state area. Then I'm going to start measuring data or recording the data. It still simulates all the data points, but it doesn't record them. And now I can see I'm in this nice steady state here. And there's a button here. If I, oh, that's the evaluate measurement again. There is a way here. Toggle measurements. So instead of typing them all in here, this toggle measurements here, you can click on, okay, the period. Now we're at 999.4 and the frequency is 1 kilohertz, which is what we should expect, right? In steady state, the frequency should be the same, and it is. Now there are other things we can measure here as well. To simulation, oh, trace, let's do evaluate measurement. Let's see what else we can measure here. Duty cycle is not something we really want to do. Let's see here. Phase margin isn't really what we want either. Okay, for instance, you can actually look at when does it cross 0. But what we can also, so I'm going to just say when does it cross 0, and it gives me the time, the exact time here. So at 4.17278 milliseconds, it is when this is at 0. And so you can actually use that to help you determine a phase shift. You can, because if you know when it's 0, you can determine what the phase shift of it is. What other things that are kind of interesting to do here? There's all sorts of measurements, and you can play them. You can do the maximum. Here, y at x value. So I'm going to say current, but then what I'm going to do is I'm going to put a time in. So I'm going to say 5 milliseconds. Whoops. And I need to make sure I put in 5 milli. And then it will say, oh, y at 5 milliseconds, which is right here, is negative 3.45178. So you see there's all sorts of little cool tools built in here. And then there's some other things here. You can toggle some cursors. So you know, you can move this up and down, and then you can see right here it gives you the x value and the y value. And what's kind of neat about this is you can kind of use this to say, okay, if you want to manually do some of this, and now I'm using the left mouse button to move this one, and you see there's a blue one. If I hold in the blue, the right mouse button, the blue one moves. And so you can kind of move these to different locations. And what's really, I think, kind of interesting or fun here as well, you know, we can do here, okay, let's maybe say, okay, roughly we're at 0 here, and then, whoops, I did the wrong one. It's easy to get the mouse button confused, and then roughly 0 there, you know, and it does y1 minus y2, which is 0, and then, you know, there's other things in the chart as well. So it's just a very nice little tool as far as being able to see different values on these graphs here. So, yeah, and there's plenty of other ones that you can play with, and I encourage you to play around with them. Yeah, there's lots of little things, but the key thing from this video here is you have to kind of analyze what is the frequency that you're given here in order to know what is the appropriate frequency, or not appropriate frequency, the appropriate runtime in order to gain all the behavior. Because see it more and more often when people are running simulations and they're like, oh, I'm running, a simulation at 1 kilohertz and nothing's coming out, because they haven't changed their runtime. They've left it at 1,000 nanoseconds. By default, it's always going to be 1,000 nanoseconds. Now, if you're doing DC analysis, that's usually fine, but AC analysis, you always are going to have to change that runtime to whatever is appropriate for the frequency or periods that you're working with.